Good morning, everyone. Hope you guys can see my screens right now. So I'm Ziping, and I'm a student in mechanical engineering. Today, I'm going to talk about my PhD research topic of developing this automatic unloading on the go system for the agricultural combine harvester, which what we call the auto unload. So I think before I get started, like I first would like to give a little bit background about what is an unloading on the go procedure for agriculture, because for many of participants here, we don't have an agricultural background. So here is on the right, you will see a video showing like what is unloading on the go procedure look like. So on the left, this is a combine harvester. And during an harvesting operation, the combine harvester will harvest the corn or soybeans here, and then store the products in an onboard container. However, when the container is full, so you need to unload the grains into somewhere else. One way to do it is that the combine harvester can drive to somewhere that is at the end of the field and dump into a container, a large bins. However, this is not efficient because you will stop harvesting. So instead, what a common practice for farmer is that it will have a tractor towing a grain cart driving alongside this combine, and then the combine will just unload the grains to this grain cart so that it can continue harvesting. In this way, it can maximize the harvesting time of a combine harvester, and thus maximize the grain transfer and harvesting efficiency. We can see that from a productivity standpoint, unloading on the go is a very good procedure for harvesting. However, there is also some downside of unloading on the go, because one of the major downside of it is a very complex operator task and can easily lead to fatigue of the operator and maybe some grain loss because of spillage. So let's see like what a combine operator needs to do when there's an unloading on the go procedure is happening. So first of all, because it is unloading from this combine to the grain cart, it needs to monitor the filling status inside this grain cart so that it can determine the next step, what is the appropriate auger location, the auger location to be to unload the grain into, so that it can prevent spillage and also fill out the cart. And also in the meantime, because these are two separate vehicles, the combine operator, after it decides what is an appropriate unloading location, it needs to next tell the tractor operator, like you go forward a little bit or backward a little bit, so that it can coordinate these two vehicles. And besides the unloading procedure, the combine operator will also be harvesting in the same time. Therefore, it needs to watch for the clearance of the vehicles, and if there's any obstacles in the fields, it to react to it, or the terrain change and etc. And also another important point about harvesting is that the corn condition could change. So it needs to adjust the settings of the harvester so that it can maximize the productivity of this harvesting procedure. We can see that the multitasking nature of this unloading on the go make the on the go very complex and exhausting. Therefore, we propose to build this auto unload system together with John Deere, and the target of this auto unload system is to automate the first three operator tasks here, which is monitor the filling status and determine where we want the auger to be, and communicate between these two vehicles to coordinate these two vehicles in a closed loop control manner. So first, I will start by introducing how we plan to do this auto unload procedure. So here is a high level architecture showing the unloading procedure. We will have an auto unload controller on the left, where you can see here, the auto unload controller basically takes the user input about how the operator wants the unloading procedure to be, and as well as some parameters set by the engineer, as well as the current system status, including the fuel status and the tractor dynamics. With all this information, there are two important information that the unloading controller is going to send to the vehicles. The first one is the auger on-off message. Basically, whether we want to turn on or off the auger. And then to simulate this process, we built an auger model to simulate when we have an on-off command, how the flow rate is going to change. And in the meantime, the auto unload controller is also going to send desired relative location between these two vehicles. And then we will have a low-level controller, which is the machine sync. Machine sync is a machine-to-machine communication technology developed by John Deere that can coordinate these two vehicles and to automatically control the velocity of the vehicles to let it reach a certain point. Therefore, we just command the points that we want the vehicle to be to the machine sync system. And then we model the dynamics of the machine sync system with the system ID approach and model how the actual location of the two vehicles going to be. And with the relative position and the flow rate, we then can model how the plant is going to, how the cart is going to be filled up with this procedure. Here we build a grain fill model to model how the grain is going to pile up, and then the output of this model is going to be the fuel profile inside the car. And finally, we will have a perception system here to measure the grain profile inside the car and feed back to the auto unload controller and close the loop around here to automate the unloading process. Next, I will talk about how this auto unload control strategy is going to work with all the models that we have built. The auto unload controller consists of two stages. The first stage is the control strategy, where it will calculate what is the desired auger location going to be and auger status. In these stages, as you can see on the upper right, there will be, if we have a grain profile feedback from the perception system, it will first divide the profile into several rows, and then it will calculate whether this row is full or not based on the fullness matrix that we define. And for example, over here, the green means it is full and the red means it is empty. After it finds the empty section, it will then fill out the car following some of the strategy that farmer usually use. One of them is front to back, which means it will fill out the front of the car and then the back of the cart. And we also have two other strategies, for example, the back to front, basically fill out the back and then to the front, as well as middle to back to front. In this kind of strategy, it will first fill up the cart to a more conservative level and then top off the cart from back to front to the desired level. In this way, this is also a very common practice for the farmers to keep the loading of the whole grain cart to be more consistent along the car. And besides the control strategy, the next step is the movement control. After the strategy decides what is the desired auger location, it needs to sense the command location to the machine sync system to achieve this kind of movement goal. There are two options here for us to do the movement control. We built an open loop controller and a closed loop controller for the open loop movement control. First, I will introduce what is the open loop controller. Basically, for the open loop controller, after it sets this desired location from the field strategy, you will directly send this location to the machine system and let the machine system move to the desired location if that works perfectly. And one thing that we noticed that here is that before we directly send this desired location to it, we will have a nudge calculator. The reason why we have this nudge calculator is that the machine sync system is not taking the desired location. Instead, it's taking a kind of nudge message, which is like it want the vehicle to move forward a little bit or backward a little bit, so that we will have a nudge calculator here, basically comparing the desired location with the current commanded location, and then to calculate whether it wants to move forward or move backward. And after that, the machine sync will take care of the low-level control to control the velocity of the tractor to move to the desired location. And then the plant is going to be change the fueling status inside the cart and close the with the large feedback loop outside. And different from an open loop approach, we also developed a closed loop approach, which in this closed loop approach, instead of directly sending this desired location, we calculate the tracking arrow with the actual location and use this and design a transfer function with a mixed sensitivity loop shaping technique to calculate a augmented desired location x tilde and send this augmented location to the nudge calculator. With this means the whole system can be more robust to disturbance and plant uncertainty. So after we building all these models for this procedure, as well as all the two different types of controller, we can simulate the unloading process. Here are the simulation of unloading process where we use a front to back strategy. On the right of the slides, you will see the unloading procedure, unloading a video of the unloading procedure. Where on top, this is open loop control, where you first move to the front of the middle of the car, and then when the auto unload started, you will move to the front of the cart. And then after each section is full, it will go to the next section. We can see that both the open loop and the closed loop can achieve the goal here. However, the closed loop control strategy have the control effort, which is the augmented desired location. We can see that it tracks the actual location, tracks the desired location better than the open loop controller. After we validating that our idea, the auto unload controller can work to automate the process of a unloading on the go procedure, the next step is we integrated everything into the actual hardware. And this is a hardware diagram showing that how different parts interact with each other during this auto unload process. On the left, you will see we implement our controller in the D-Space micro auto box, and this auto box is going to be installed on the combine. And the Autobox has 3 different interfaces. The first interface is it interface with the combine CAN bus with the CAN interface, where it receives the current vehicle status and also sending the 2 commands to the whole system, including the position command and the auger on-off command. And then with the position command, the combine is going to coordinate these 2 vehicles with the machine-sync wireless system. And in the meantime, it also has an Ethernet interface communicating with the perception system. Basically, the perception system, it needs to relay the current vehicle status to this perception system and also receives the current fuel profile and impact location kind of useful information from the perception system. And we also developed a testing user interface for the test where the user can monitor the system status as well as giving the input to the system to tune the different configurations. So here we will first show like how does the perception system used in this system looks like. So here is the perception system. We will see on the left of the figure, this is the stereo camera, and this is a stereo camera based perception system. What it monitors, the most important thing it monitors is the grain profile. On the right, you will see a grain profile returned by a perception system during an unloading process. We can see that when the unloading started, the grain pouring into the grain bed, we can see the whole profile, especially on the back of the profile, start to grow. And this is the information that we would like to get from the perception system. And then we also have this user interface where for this user interface, the user can not only like configure different settings, like the desired fuel profile, different fuel strategy, as well as just monitor what's happening in different components of the system, and also monitor the fullness at each section and the fuel profile returned by the perception system. With all this developed and configured in the combine cap, we will go and show you a video of how does it look like when we have the testing. So here is a 3x speed video. We can see that during the harvesting, we will have the wheel into auto steer, and what the combine operator only need to do is just to push the button to start the unloading process. And we can see on the left, the auger will be automatically controlled by the auto unload controller to fill out the car from the middle to back and then to the front. And we started from a half full grain car and we used the open loop movement control strategy. And we can see after you reach the front of the cart and everything finished, you will turn off the auger. We can see the final profile of the car here. And then besides looking at what is happening in the cabin, we can see like during the same process, what is also happening to the different part of the component. So on the right side, you will see how what the stereo camera sees the whole unloading process. On the right, top right, it is the grain profile returned by the stereo camera. On the lower right, you will see a stereo camera view, the rectified image of the stereo camera, where it starts from loading the back of the cart and then gradually move to the front of the cart. With the grain is being loaded, you can see that the profile returned by the stereo camera becomes higher and higher. And then it will move to the next section and finally stop unloading here. So we can also see how the controller is react to all different kinds of messages returned by the stereo camera. In the left image, you will see that the blue line is showing what is the relative location between these two vehicles, and the orange line is showing that what is the fullness calculated by the controller based on the fuel profile returned by the perception system. We can see that in the beginning, the auger is moving to the center of the cart, and then it found that this section has already been full, and then it will move to the next section at here, and it is not full, and then it will inform the operator to turn on the auger. After you turn on the auger and it becomes full, it will move to the last section, which you will see in the videos here. It will move to the last section, and then it will increase the desired fullness because we introduced before. In the first round, in the first pass, it's going to be more conservative, and in the last round, it's going to top off the car to desired fuel level. And then every time the measured fullness reach the desired fullness, it will go to the next section and so on and so forth until it moves to the front of the cars and finish filling up the whole cart. So that's all for my introduction of my project on automating the unloading on the go on combine harvester. And this is a joint effort of a whole team and different department and different professors.